Hi everyone, and thank you for your time. My name is Rudian, and I'm going to be presenting work I've been doing with Amir on detecting vertebrae in full spine scans, which we've called the ladder algorithm, or finding repetitive structures in medical images by induction. This paper concerns automated vertebra detection, in particular in the case of whole spine magnetic resonance scans. There's previously been a lot of work in vertebra detection in lumbar, i.e. lower back scans. Several examples are cited here. However, none of these works generalise to the whole spine scan case. And the reason for this is probably due to a lack of training data. Lumbar scans are comparatively common because the most common site for back pain is in the lower back, and as such most routine clinical scans have this in their field of view. Acquiring a full spine scan is more difficult and requires stitching together several different scans of different fields of view. However, it's necessary in the case of several serious diseases such as ankylosing spondylitis, bone metastases, and multiple myeloma. And as such, vertebra detection in these scans is very important if we want to achieve automated diagnosis in any of these diseases. Here, we propose a method to detect vertebrae in whole spine scans using only lumbar scans as training data. Before talking about our method, I'd like to motivate why detecting vertebrae in clinical scans is important. Firstly, finding vertebrae in medical scans automatically has been shown to be an important pre-processing step for the automated diagnosis of several spinal diseases. Systems for several diseases such as disc degeneration, central canal stenosis, and scoliosis have had as a pre-processing step vertebral detection stages, and several of these are cited below. Secondly, vertebral detection allows us to perform large-scale studies into the variation of the vertebral column across a large population, which wouldn't be possible if we had to manually annotate every single scan. Finally, by detecting vertebrae, we can also detect other spinal regions of interest, such as the spinal column or ribs. These detections in turn can then be used for downstream tasks. During the experiments in this paper, we considered two different types of spinal scans. We train our method exclusively on lumbar field of view scans, as shown on the left-hand side of this slide. We then evaluate our method on both lumbar scans and also whole spine scans, as shown on the right here. Vertebrae change size, rotation, and shape as we move up the spinal column, and we need to be robust to this, despite not seeing these variations in our training dataset. All scans used here are clinically extracted, which means that they tend to have several sagittal slices concatenated together. Also, because the scans are extracted in clinics, we notice the wide variety of different imaging protocols used. For example, we have MR weightings of T1, T2, stir and flare, as well as a wide range of different resolutions in both the sagittal, coronal and axial planes. To be able to perform whole spine segmentation of vertebra with only lumbar spines as training data, we wish to leverage the repetitiveness of the human spine. By this, I mean that if we know the location of a certain vertebra, this gives us a strong prior on the location of the next vertebra in the vertebral column. It should be noted that this isn't unique to vertebra, but occurs in several different structures within the human body, such as ribs and teeth. As such, we believe that our method could be extended and generalised to such cases. The proposed ladder algorithm uses a simple iterative procedure to detect vertebrae moving up the vertebral column, starting at S1 and terminating at C3. We initialise the algorithm by feeding it a patch around the S1 vertebra, as shown here. This patch around S1 is given as input to a convolutional neural network, which will predict the coordinates of the corners for the S1 vertebra, and also predict the coordinates for the corners of the L5 vertebra above it. The coordinates for the S1 vertebra should be fairly accurate as the patch is centred on S1, and as such we save these as the coordinates as our final prediction. The coordinates for the L5 vertebra are less accurate, and fairly often the network predicts outside of the patch. As such, we use these coordinates to extract a new patch, this time which should surround the L5 vertebra, the next vertebra up in the vertebral column. Again, we feed this patch to the same neural network, which will predict the coordinates of L5, and this time the vertebra above it, L4. Again, we save the coordinates for L5, and we use the predictions for L4 to extract a new patch. And we can continue iterating up in this fashion, moving up the spine, with each iteration both extracting the locations of a vertebra and also proposing a patch surrounding the vertebra above it. This method has analogies to proof by induction, where we show that if a property is true for the nth case of a sequence, it must also be true for the n+1th case of the sequence, using knowledge of how the sequence was generated. The simple convolutional neural network architecture used to extract the corners of each vertebra in each patch is shown on the right here. Training this model is fairly straightforward, and we use Genadisk, a large dataset of over 4,000 clinical lumbar scans from around 1,800 different unique patients. All these scans are clinically extracted, meaning that we observe a wide range of different lumbar pathologies, as well as different MR weightings such as T1 and T2, and also a wide range of resolutions and other scanning protocols. In each scan, the corners of each vertebra from S1 to T12 are marked by a radiologist, making 7 vertebrae marked in total. Whilst training this network, we have 2 different options of training regimes. We can either ask the network to predict each vertebra in the entire chain from S1 to T12 at once, and then backpropagate through each example, or alternatively, we can use teacher forcing, as in the traditional recurrent neural network example, where we give the network the nth vertebra and ask it to predict the location of the n+1th vertebra. In practice, we use a mixture of both of these to train our network, and this increases the amount of training data it receives. At test time, we can initialize the algorithm using a previous method of automated lumbar vertebra detection to find the S1 vertebra. We then extract a patch around that and use that to initialize the algorithm. In our experiments, we used the method of Lutus et al. Proposed in 2013 to extract S1. Going from the lumbar scan training examples with 7 vertebrae to the whole spine scan cases with 23 vertebrae is as simple as just updating the algorithm to run for 23 iterations instead of 7. Here we show an example of the network being used on a full spine case. On the left-hand side you see the vertebra around which a patch is extracted. In the middle we can see the predictions of the network in that patch. And on the right-hand side we can see the locations of these predictions in the frame of the original scan. As you can see, the predictions of the network are very accurate, and it bounds each corner of each vertebra very well, even as we move up towards the top of the spine. Quantitatively, we evaluate the performance of our detector on both lumbar and whole spine scans. For the lumbar spine case, we use the testing dataset of the Genadisk dataset we used for training. This consists of 480 clinical lumbar spine scans. For the whole spine case, we use OWS, or Oxford Whole Spine, which consists of 64 labelled clinical whole spine scans. Following definitions previously used in automated vertebra detection literature, we consider a true positive detection as when the centroid of a predicted bounding box is contained entirely within a single ground truth bounding quadrilateral. Under this metric, we report the recall and precision of the detector, We also report the localization error, which is the average distance between the centroids of the predicted bounding box and the ground truth bounding box. To show that the corners detected by the network match highly with those predicted by the radiologist, we also report the dice score of the overlap between the two quadrilaterals. As you can see, we achieve high accuracy with an average of 99.8% precision and recall in the lumbar case, and more importantly, there is only very little drop when we generalise to the whole spine case, going from 99.8% accuracy to 99.4% recall and precision in the whole spine case. In this slide, we show several different outputs from the network across a wide range of different whole spine scans. As you can see, the network can deal with a wide range of different curvatures and appears to detect the corners fairly accurately in all cases. There are, however, several failure cases of the algorithm, and these almost exclusively occur in the whole spine case when we meet pathologies that we will not have observed in the lumbar spine scans. For example, collapsed vertebrae and fused vertebrae are far more common at the top of the spine, and as such are much more prevalent in the whole spine dataset. When the network meets a collapsed vertebrae, as shown in the bottom left panel, it completely ignores it, instead skipping on to the next vertebra. When the network meets a fused vertebra, or two vertebrae fused together, it seems to predict them as a single vertebra, and the corners of the detections are completely off. Finally, we ran into a problem where occasionally the method we used to initialize the algorithm to detect S1 would occasionally detect L5 as the first vertebra in the vertebral column. However, this could easily be fixed by using a more modern, more accurate method to detect S1. Before concluding, I'd quickly like to talk about extending the algorithm to work with multiple sagittal slice scans. So far, we've only considered a single sagittal slice case. However, the extension to multiple slices is fairly trivial. We can do this by initializing the algorithm across several slices and observing at which levels the predictions in a certain slice diverge significantly from the predictions in all the other slices. If there is a large divergence at a certain level, then we assume that the vertebra is no longer visible in this slice and we discard all other predictions in that slice above that level. By doing this, we can build up a 3D model of the spine, as shown on the right here. This extension actually offers extra robustness because it gives us multiple estimators of the location of each vertebra. Thank you very much for listening to my talk. Amira and I would like to thank the contributions of Andrew Zisman and Dr. Timur Kadir, with whom we had many helpful discussions during this. I'm also grateful to Cancer Research UK for funding my studies, and Amira is grateful to Project Grant ISBI for funding his. Finally, we'd like to thank the Project Ginadesk for providing the data for this project.